Hi. So in this particular paper, what I need to do is in this journal, I have a data set somewhat like this, where there are duet performances, there are quartet, there are four people playing, there are many people playing, around five people playing a performance. And what we do is we separate them into the video and the audio part. In the video part, we do pose estimation. So pose estimation is like we use this particular library called pose. So this is a pose estimation library which kind of recognizes the pose in which we are walking or talking or stuff like that, so the moving thing. So it's already written in this particular thing. So we calculate the number of people, and then we just try to understand how they're moving. From that data, we try to estimate the visual beats. Visual beats is like the motion beats of each individuals. So once we get the visual beat from the musician's body, then also we get the audio beats from the musicians, what they are playing. So we have the audio beats, and we have the visual beats and the audio beats together. And after we have them, we use three algorithms, that is the swarm, the Kuramoto, and the Janus. So I have already given the links for this study. So these are the links for those papers, so you can those algorithms. So if you can browse over here, so this is the swarm algorithm, which where the concept is that I consider each of my musician to be a separate oscillator. Oscillator means a separate source of music. So where did you go? Okay, so this one, each of the musician will be like separate signal, so they will generate say a separate thing. So and then I try to synchronize them using this swarm equation, Kuramoto's equation, and Janus equation one by one, and try to measure their performance, whose performance is best and who has the worst performance. And then after getting those data, so I will get some data like let me show you. So I will get some data, something like this. This it will be like the first person, then the second person, then the third person, the body motion data. So I have a beat over here, I have a visual beat over here, and also have some audio with it. So maybe the audio beat is somewhere down here. So I get this time, the time of the beat. So maybe it's at 0.2 seconds, and this one is at 0.5 seconds, and so on. So I use these times to synchronize each one of them, and then produce a tap sound, like a drum sound, drum kick sound, with all this all this particular let me show you the drum kick sound. Yeah, so somewhat like this. I don't know if you can listen to that. So this is a drum kick sound which we play on every beat. So whenever the person is singing, or means the performance is happening, there will be a drum sound on each and every beat. So now what happens, we get the beat, and once we have this beat, I have made one kind of instrument where it press a button over here in the keyboard, and it produces that drum beat sound. So once the drum beat sound is produced on each beats, now what is the problem is it is not on time. Okay, so once the tap sound is produced, that is not on time. So how to make it on time? So we have to do some kind of post processing, like making understanding that how much delay it is taking from receiving the signal, running the algorithm, and then taking out at what time the beat should be. So there is a delay between all those wires, and information transferring from one place to another. So to get the delay, we can set maybe 2 seconds for my PC, but it can be different for other PCs. So what we did is we used a microphone, which is a condenser microphone. These are used for in studios for recording guitar sounds and stuff like that, where there is instrument sound. So we use a microphones, the condenser microphone, to record what is the output we have. And now we use a library called Splitter. So Splitter is a library which separates voice from voice from drums, and drums from others. So we can separate all those tracks into some stems. Stems are individual tracks. So once we separate them using using Splitter, so now we have the original song and our tap. And now we try to see that how much delay is there between those two outputs. And once we do it using the dynamic time wrapping. So I can show you the dynamic time wrapping. Okay, I have the link over here. So once you click on this link, the dynamic time wrapping, so we calculate the delay in between those, my target and thing. So once we get the delay, we send this value back to our tap producing sound. So that means the function, so that it can adjust how much delay there should be for producing the tap into the so that it's on correct time. So this is a continuous process. Once it is once the delay is 0, so we stop sending the message. That means we adjusted the value, what is the delay in our whole system. So this is the whole idea of making a tap sound based on the human motion, the video and audio data, and using these three algorithms. And we see that Kuramoto and Swarm performs much better than Janus. And I will give the output later on. I will discuss about the output later on. So we have the thing. So this is the whole architecture. So we have the performance, we split it into video and audio. So the audio has pose estimation, then optic flow, which is for getting the motion in the pixel. Once we get the pixel, we do some peak detection to get the visual bits. And for bit tracking, we use direct libraries like Libros and Obio. I have already mentioned them over in the document. And next we use this informations into these three algorithms: Swarm, Letter, Kuramoto, Janus. Also I have given the link. Now once we have that, we after synchronization, it produces a tap sound. So once we get the tap sound, there is some delay in the tap sound because of so much of processing time. So to compensate with that delay, what we do is we isolate the tap sound from the song back again, and try to understand how much delay it is. Once we understand the delay, we use a method called dynamic time wrapping. I have given the link as well. So we get the how much delay is there in between the original song and the played song. So we adjust our machine time according to that dynamic time wrapping, so that we can understand that how much delay there is for processing the data. So this is the whole architecture about the paper, and if you have any doubt, just let me know. I will answer them as well. Thanks.